Welcome back to Advent of Code 2023, day 23, which opens in 1 minute. Alright. So, still haven't finished 21. My god, 21 is such a mess. I need to do some offline work and make sure all my formulae are correct. I don't want to do that on stream because it's like better with pen and paper, but what a mess. Got little animations here. Lava. What was that? Gears or something? Sand. Eventually we'll get snow. Oh, I haven't opened up my IDE. Alright, 23 it is then. A long walk. Oops. Hang on. There we go. A long walk. The elves resume water filtering operations. Clean water starts flowing over the edge of Island. They offer to help you go over the edge of Island too. Just hold on tight to one end of this impossibly long rope and they'll lower you down a safe distance from the massive waterfall you just created. As you finally reach Snow Island, you see that the water isn't really reaching the ground, it's being absorbed by the air itself. It looks like you'll finally have a little downtime while the moisture builds up to snow-producing levels. Snow Island is pretty scenic, even without any snow. Why not take a walk? Oh, okay. So it's unrelated to the snow and the water. We're just taking a walk through a forest. Alright. There's a map of nearby hiking trails that indicates paths, forest, and steep slopes. Alright. You're currently on the single path tile in the top row. Your goal is to reach the single path tile in the bottom row. Because of all the mist from the waterfall, the slopes are probably quite icy. So you have to follow the arrows, okay. To make sure you have the most scenic hike possible, never step onto the same tile twice. We're trying to find the longest path. Oh, what was the algorithm for this? There's an estimation algorithm, which is where you, Was it an exact algorithm? I can't remember now. Longest hike. So it's the standard textbook problem. Alright, just make sure let's do the necessary things. So okay, so the input is there. The in and the exit is there. It's in the same locations. Alright. Oh dear, 21. Alright, so... We've had so many grids these past few days. So we can reuse pause. You can reuse quite a bit of this code actually. All right. Get parity. All right, so grid dot append line dot strip. All right, so start equals pause. So it's going to be row 0, column. Should we just find it even though I know where it is? That way we can generalize inputs. So it's going to be grid 0 dot find dot goal equals pause. Right, so let's make sure we got the nm. It's going to be this. So it's going to be n-1 grid n-1 dot find dot print n. Okay. Right. Why are these not single quotes? Just use single quotes. Alright, take a look. One for one. We often have 1 for 1. But last time we had 1 something. Alright, 131. So we start at 0, 1 and 140, 139. Okay, right. So find longest path. There's a directed graph essentially. No, well, yeah, directed graph, but most edges are bidirectional. Hang on. So we're allowed to step onto the arrows, and that counts as 1 step, right? Or do we skip ahead? I see. Your next step must be downhill. So if we step onto an arrow, then we must... continue, but it counts as 1 step, so... Okay, so we want get neighbors. So it's similar to before. For delta in, yep, for those directions, neighbor is that. If we are inbounds, if it's not a hash, yep. So we yield it if it's, we also have to check if it's Alright, if grid pos.row pos.col equals that and delta is not equal to pos, so it must be 0, 1. So if it's not, continue. So 1, 2, 3, 4. So what are the symbols? It's going to be so assume it's that. -1, 0. Is it a small v? Yeah. Delta, so if it's v and delta is not equal to, so it's 1, continue. Okay, so we're not allowed to move in those directions. Yield neighbor. All right. Just test this out. Print get neighbors from start. Print, just get it as a list. Whoops, that's not how you do that. List. One. Yep, okay. So, what do we do now? What we do now is grab my coffee. Okay. Longest path in directed graphs. Isn't this just... Can you just do depth first search, but you don't... But you, let me Google this. I think you just do depth first search. Longest path to goal in directed graph. It's an MP hard problem, isn't it? But if we've got... Yeah, it's an MP hard problem. If it's acyclic... It's not acyclic, is it? I don't think there's any cycles, in which case, If there's no cycles, then what do? We just... Longest path ending at V may be obtained by the following steps. Find a topological ordering of the given DAG. Shortest... G minus... Okay, G minus negative G is... It's like you take the graph, but you change every edge to be negative. And if you find the shortest path in that, that is the longest path in G. But how do we... Oh, I see. Interesting. So we use... Okay, sorry, I didn't have the browser open. We want to run shortest path. So not breadth first search, is it? It's going to have to be Dijkstra? Because it's negative edges, but then... I don't know, we can try running Dijkstra. So... The distances are negative, basically. We're trying to find the... Interesting. Should I copy some of my previous Dijkstra code? I know I said I always try to write it from scratch, but I'm feeling a bit lazy today. Especially because I've got another problem hanging. When did we last use Dijkstra? It was like... Here. Okay, but most of this we don't need. Okay, try and... so we need a priority queue. We're not going to do A star. Let's do Dijkstra. From a start pos to a goal pos. Don't need any other parameters. Don't need an H. Go away. Does it make sense to have an H? No. Because it's always possible to have a long path that goes everywhere, so you don't know anything really about lower bound. Alright, get neighbors, we already have a get neighbors method, so that cut that whole thing out. Okay, queue equals priority queue. Dist from start 0. Queued.put dist start. We don't need H. Start. Okay. While not queue.empty. So we've got fdist current state queue.get. If, so let's just call it current. If current is goal, is goal. Well, does this actually work with negative edges? I guess it does. It's just as long as you don't have negative cycles. I don't think we'll have negative cycles. So return dist current. If okay, so if this distance is bigger than what we have stored, then this is lazy deletion. So continue. All right. So for neighbor in get neighbors current, so that will get us the neighbors. Gdist equals dist of current plus, it's going to be -1. -1. We're using negative edges. Okay. So if neighbor is already in dist and we already have a lower dist, skip this one. Otherwise, update dist equals gdist, q.put dist neighbor, there's no h. So, is that it? Does this... it feels weird, but I don't remember doing this before. I guess this is what you do. So the shortest path in the negative graph would be the longest path. Okay. Print Dijkstra start goal. Oh yeah, we need less than. Just do that. And is it infinite? Great. Oh, of course there's cycles. Damn it, hang on. Of course there's cycles. We can literally just go back and forth. How do we stop that? Do we just want to... not go somewhere we came from before? They're actual cycles here. I don't know. So I think we just have to keep track of where we were before. So that we don't go backwards. So we have to store so technically this shouldn't work on a graph with cycles, which our graph is, because a single undirected edge is a cycle. You can just go back and forth. If we just ban ourselves from going backwards at each node, then that solves it, doesn't it? How do we do that? We just have to say, that's why, okay, we need a came from. Okay, came from. Alright, so current. Oh, blah, blah, blah. Alright, if... So if the neighbor... If neighbor is where we came from, don't go there. No. If... Yeah. And when we put it in the queue, we want came from neighbor equals current. Will that just work? -2134. What was the question? How many steps long is the longest hike? So is it 2134? So we finish on the goal. Correct. Okay. As you reach the trailhead, you realize that the ground isn't as slippery as you expected. You'll have no problem climbing up the steep slopes. Now treat all steep slopes as if they were normal paths. What? So we just ignore the, Isn't that just the same? Oh no, but there's gonna be cycles now, aren't there? They've done something sneaky, I assume. Like, you would think this will just work if we... because it doesn't matter? Alright, let's try it then. It shouldn't matter unless they put cycles that I didn't spot. Okay, so this is... get neighbors... let's say 1. Let's say neighbor func. So we use neighbor func. So part 1, use get neighbors 1. Alright. So here we just use get neighbors 2. If there's no proper cycles in this, no loops, then I don't see why this is harder. It seems to be equivalent. In fact, if anything, it's easier because then you don't have to deal with these. You take these out. So you would just do... let me guess, is there a cycle? Yeah, probably. Let's test on the smaller input then. If there's a cycle here... Probably a cycle here too. Have a look. Yeah, yeah, there's cycles. So what do we do? So now it's a true... It's actually an NP-hard problem. But we might be able to find a way of... making it work, so... So that's the longest path. Bloody hell. Do we want some sort of recursive? Well... So if it's acyclic, we do this. That's what we did. Approximations. I mean, I've studied this stuff before, but if it's cyclic, if it's not acyclic, it's not the same as saying cyclic. Cyclic would mean it's one cycle, I suppose. Basically, just use backtracking or something, I suppose. And just pray. I mean, there's not much branching. Oh. You just use backtracking. Alright. I don't want to use recursion because that's... You need to... You don't want... You want to, keep track of the visited cells so that you don't revisit them, and with recursion that doesn't quite work. Okay, so backtracking it is then. Tracking on start to goal. Alright, so we'll use a stack. I did already have my coffee. I can't have another one. I've had too many. Alright, how do we do this again? This was one of the first proper algorithms I kind of wrote in Python because it was for my mathematics degree coursework. I had no idea what I was doing, and I wrote a horrific, hundreds of lines long thing where it had lots of pointers and removing... They didn't really teach us how to use data structures properly in any language, so... But now I can use the data structures properly. Right, backtracking. So we want to say I get how to do this. Basically, we're turning at every possible junction, but we're keeping a set of visited. So we never visit the same place twice. So visited equals, I suppose we should put start. We never want to. All right. So while, wait, Q is not the right thing to do here. What are we trying to do? Yeah, okay, this is fine. While Q. So current equals Q dot pop. All right. We look at all the neighbors that we can go to. So we do but how do we deal with the visited set? I forget how to do this now. We go through so if it's already visited, we skip that one. We don't need to do this. We say what? So it's now visited. We now want to look at each of the neighbors. If neighbors visited, skip that one. So we see a new neighbor. Also, alright, so if current equals goal, max distance to goal equals max of whatever steps we're on, and the previous. Oh, okay, I'm sort of getting it now. Because it's a stack, we can incrementally change visited. Okay, so this will sort of work. All right. Current. Okay, so this means we take a step. So steps plus equal 1. All right. We go to current. The neighbor in get neighbors 2. Hang on. All right. I think we want to store the steps as well, along with the Okay, so we're standing on start. We don't need that. So current and the steps we took to get there is that, right? If it's gold, then we do that, fine. Visited.add current. But when do we remove current? When do we remove current? I can't remember how to do this now. Let's think this through. We're putting nodes on the stack. Each time we visit a node, then what? When do we remove from the stack? When we're backtracking. When are we backtracking? It's when there's no more neighbors to uncover or something, I don't know. Because all neighbors are visited. I can't remember how to do this. I don't normally do it this way. I normally do it recursively, but this way the visitor set is throwing me off. Okay, so you take a node, you look at the neighbors, but you ignore the ones you came from. Fine. And you put each of those neighbors on the queue. The moment you come to a node which has no more neighbors, because everything's visited, Then you remove. Okay. Got it. So go back. So we don't need to store the steps here. So current is q.pop. Alright. No. Q -1. We don't take it out the queue. You only take it out the queue when we've explored all possibilities. Alright. So we look at what's at the end of the queue. We don't need to do this. Oh yeah, we can. Okay. And then we don't need to do that. Do we? Hang on. No. Maybe. Yeah, we do. We're visiting this. Current, and now we're looking at its neighbors. So neighbors equals neighbor or neighbor in. Get neighbors current. If neighbor not in visited. Right? If not neighbors. So this means we're backtracking now. So we do q.pop discard current steps -1 visited.remove current. Otherwise, we put all these neighbors on the stack and we increase the step. Yep, this makes sense. Okay. For neighbor in neighbors, q.append neighbor. Do we actually visit them? No. But we do add one step. So when we now pull out the next neighbor, the step will have increased. We visit that neighbor and then we do the same process. So if we do this, we're basically going down every path. And then once we've done that, would it just be this? Now, how long will this take? So we go until we take start out. That means, wait, why wouldn't we just put neighbors back in when we pull start out? Oh wait, something's wrong here. Damn it! This would just go infinite loop, wouldn't it? There's no neighbors, but there will be neighbors because we've removed them again. So when we backtrack, how do we stop ourselves from going back down those paths? What tells us we've visited them? I don't understand this. Let's just run it. It should infinite loop. Yeah, it will. Okay. Come on, try and get this right. So what tells us we've already been down the path? I forget how this works. Because we can't just... We're allowed to revisit nodes along all these paths. We're just not allowed to revisit them within one path. So we can't just hash them or whatever. I think there's a notion of direction here. Well... Maybe we shouldn't keep current here, but then how do we know what the steps are? I suppose we just store the steps along with... Could just resort to writing it recursively, but oh, I don't remember how to do this. Should we write a recursive method then? If you're going down a maze, well, you would use directions to know which way you've come from, so you'd know not to go down that path because... So it's like you turn every left. Maybe I gotta look this up. Always uses recursion. I think I'm trying to do this in too iterative a way. I think I should be using recursion. Alright, should we just write it recursively? I mean, it's going to be much simpler. Alright, I don't remember how to do it like this. Let's write it again. It's fine, backtracking, so... I don't like passing this visited thing around. Like, ideally, you would just be adding and removing from visited as you're walking back and forth. I don't see a way to get around that with this, maybe because you need a... I don't know. We'll just do this the slow way then. So we got... So... From a start position to the goal and a set of visited nodes, right? So we do this again. Well, neighbors. Neighbors equals neighbor for neighboring, get neighbors to start. With neighbor not in visited. Alright. So for neighbor in that. We can make it a generator or whatever. What am I trying to do here? What is backtracking supposed to return? Just longest path to the goal. Okay. So find longest 0. None. 0 is misleading. Alright. Let's say B equals, so we run backtracking recursively. So it's going to be from neighbor to the goal. It's going to be visited plus start. We're not allowed to revisit start. Okay. If B is not none, longest equals max of longest B. Return longest, but we haven't dealt with the goal. If start is goal, return 0. We have return longest plus 1 because we took 1 step to get to that neighbor. Is that it? See, that's much more concise. It's just I don't like recreating visited every time. That seems inefficient, but whatever. Rent backtracking start. Oh, is that it? Just duplicated that line. I don't think so. Oh, and visited. So just an empty set to start with. Just hide this. Hide that. Unsupported operand type. Visited. It's okay. It's vertical line. Oh. If B is not none. If longest is none, longest equals B, else longest equals max B longest. Okay. Return longest plus 1 if longest is not none, else none. I thought it would deal with the nuns correctly. Okay, 154? That's correct. But I'm worried it's just going to take a really long time for the big one. Yeah. Recursion limit. Do we dare increase it a little bit? Recursion limit is 1,000. See, that we wouldn't have this problem if we were using it in explicit stack. What kind of limit would make sense? 2, 1, 3, 4 was the longest path before. So, a few thousand. Oh man. Let's go for 5,000. Don't crash my computer. Really? 10,000? Seems like it might be okay. Okay, my computer is going into overdrive. I don't think backtracking would work, but we need to be smarter about this, maybe. Should we be eliminating dead ends or something? Like find all paths that don't lead anywhere and cut them off. Let's just see what it does. Should I also be using hashing? Well, visited set is the problem. You can't, there's no point using hashing. Caching, I mean. I think we might need to prune. How do you prune? You need to find dead ends. So you need to find a leaf node, which is just like a... We want it to only have the cycles and not the dead ends. Are there any dead ends? I don't even see any. So dead end would be a dot which has only one dot adjacent to it, excluding the start and the goal. So for example, you could start pretty far in. You don't need to start at the start, but I don't know. That's not a problem. We're not branching there. Okay, this recursion limit seems fine. It makes sense because 141 times 141 is what, 10,000 something. So we're never really gonna have be down a path that long. Should we just... Alright, stop. Print length visited. I want to see what paths we're getting, if any. Because one of those might be the best one. Okay, we found 14674. The longest we found... Wait, so visited would mean... Yeah, the length of visited is exactly the path length. 5094. is the best. 5138, 5298, 5362, 5522. So the best we've seen is 5522. Five 614. Can we beat that? Should I just try these? I'm not finding many new pods. Oh, okay. It was just stuck in one lengthy one, I guess. See, that was close. 5718. I could be... We should really be... Okay, whatever. 5718. So I just gamble. 5718. Oops. Didn't type there. What does that do? No, it's stuck in a long part. So I just try 5718. It's, I mean, it still gets very close, so it's probably not correct, but I'd rather finish this if I can. 5718? No, it's too low. We can try pruning, but then I don't know what. I don't see anywhere we can prune, not visually. It wouldn't really matter so much, I guess, but I think we've... See, one thing we can do is split this into junctions, because we don't care about these sections here, right? Because you don't need to do recursion for each of these steps. You know when you get to a junction. So we can condense this graph into components. Where, and those are all distances. and then just find distances between them. That probably is the way to go. I can leave this running for a bit. Thing is, I gotta watch it because you might see a bigger one. Alright, so what do we want to do? We basically want to change this graph, get rid of all these lengthy lines. We just want to change it into a node of junctions and the distances between them, right? Probably want to use right, I have an idea. Right, don't use this. Okay, I'll just keep watching this, see if we get any bigger numbers. Alright, so keep that there. We want a graph so we want nodes, which are going to be positions. Excuse me. So if we add an edge from U to V with a given distance, so we need two graphs. We need these. So this can be a default dict. Set, we can import that. So if we add an edge from U to V with distance D, that's basically the same as saying self.edges U add V and the other way around. And then we want the dist. Self.dist, so it's going to be square brackets equals D and the other way around, V and U. Okay, so that's when we add an edge. So So we want to accumulate a list of checkpoints, as well as the start and the goal. So let's say call them checkpoints equals this. We can put start and goal in there. For I in range and for j in range m, we want to check if something has so it's going to be 3 or more neighbors. That means it's a junction. Yeah, this is going to condense the graph so much. So it's like... Okay, so if length of get neighbors 2 for pos ij is greater or equal to 3, it's gonna have to be... Okay, fine. Checkpoints dot append pos ij. Okay, so that will be our graph. All right, those are the nodes of our graph, but we need to figure out what the edges are. So for this, we do a mini breadth first search starting from each checkpoint. So depth first search even. For checkpoint in checkpoints. So just let me just branch out until we find the first node we hit and then stop there. Q equals, so visited equals empty set. Q, we start from that checkpoint. Should we make this a set? I don't know. Then we can quickly find if something's a checkpoint. Okay. Okay, so Q... Alright, while Q. So current equals Q dot pop visited dot add current for neighbor. So for neighbor in get neighbors 2 of current. Alright, so if it's a checkpoint, wait, if neighbor in visited skip, this one. If neighbor in checkpoints, then we at the edge, so graph dot add edge. So we add the edge from our original checkpoint to this neighbor. Distance, damn it, we need BFS for this. Okay, fine. Q, import Q. Okay. You get, so we want, don't need that. All right. If neighbor in dist, that means we've already visited it, continue. If neighbor in checkpoints, then graph.addEdge checkpoint to neighbor, and it's going to be dist of checkpoint plus 1. That is the distance to that neighbor. All right, so we add that edge and continue because we don't want to expand. We don't want to put that in the queue. Otherwise, queue dot. So then we just do dist neighbor equals dist checkpoint plus 1. Q dot put neighbor. Yeah. So we do that from every checkpoint. And it won't matter if we've repeated edges because it will sort that out. It would be redundant. So now we should have the distance between every pair of checkpoints. So then backtracking should operate on these checkpoints instead of what we were doing before. So add that out. Yeah, okay, we could hide that. So this time, backtracking start, goal. Alright, so we're not using... So instead of get neighbors, we're just getting neighbors from this graph, so... Let's find get neighbors. Return list of self.edges. So for a given node, edges u. Okay. So instead of get name, so it's going to be here. For neighbor in graph.getNeighbors start if it's not visited. B equals backtracking there, blah blah. Okay, but the edge is not distance 1 anymore. So what do we do here? Longest equals none. So we do longest equals graph.dist from start to neighbor. Graph.dist. Oh. Hang on. D equals it needs to be that is a hash map. Got to put that as a tuple. Alright, longest equals D. D. Return. No. We go back to what we had before, but we want to add plus D and take this off here. Yeah, that's it. Because the D needs to be compared here. You know, that might have been a slight inaccuracy in the previous one. Alright. Alright, stop whatever we were doing before. Try again. So now... try running it. Priority queue. Am I using Dijkstra at all? No, I am, still. We still need that. Okay. Stop. If start equals goal... Hang on. Don't do it here. Result equals longer. Put it there. Return result. If start is goal, print result. I just want to see what kind of results we get. Okay, run. Alright, do we hit the goal? If we're not hitting the goal at least soon, then something's wrong, because it should be faster than that mess we had before. So we shouldn't need that much recursion limit this time. Let's change it to 5,000 or something. Okay, something's wrong then. Fine. Let's have a look at the edges. What the heck? We've only got the start and the goal. Okay. For checkpoint and checkpoints. Okay, we didn't get any checkpoints. If length list get neighbors to pos ij is greater or equal to 3. And that must happen, mustn't it? We follow this path. There must be places where this happens. Okay, here. It says 1, 2, 3 neighbors. Why doesn't that flag up here? Is get neighbors just wrong? Interesting. Hang on, stop this. Alright, so something's wrong with the get neighbors? What if it's greater to 3? I don't know. Print. Just print that and length list. Alright, let's just see what. Zeros, yeah. What? There's nothing more. No, okay, there's 2s. Wait, how can there be 1s? Why there's so many 1s? Zeros would be the hashes, I suppose. Well, it's the skip. If grid ij equals hash continue. So we shouldn't get any zeros now. Okay, so it's mostly 2s. No 3s? Alright, so I think there should be a 3 at... like here, for example. What is that? One, two, three. So what is that? That's I equals 5. J equals 41. 541. Row equals 5. Also, okay, yeah. Row equals 5. Column equals 41. 3. If there's at least 3 checkpoints dot add position ij. Okay, so there are 3s. You know, it says the row and column at the bottom of the IDE, right? Could have just subtracted instead of counting. No, that's what I was using. Yeah. I was using that down in the bottom and subtracting 1. Wait. Yeah, 42 minus 1. But, yeah. Hello, DIJ. Welcome. I'm, it's not conceptually difficult problem, but it is an NP hard problem, which means it's one of those problems that's supposed to be not solvable in polynomial time and not solvable in a reasonable amount of time. So you just gotta do clever stuff to simplify it. Alright, there's definitely a mistake here. If checkpoints.add was ij. Checkpoints equals start, goal, checkpoints.add. So how many junctions do we have? This many. Okay, fine. Oh. It looks like... Okay, so we've got checkpoints. That's fine. Don't need that. Now we have to do this. So dist equals... checkpoint 0, Q is our Q, put checkpoint on the Q. While, oh, I keep making this mistake. While not q dot empty. Because for stacks you do while not q, while q. For queues you do while not q dot empty. That was the issue, right? There we go. Okay. So we have edges in our graph. Fine. That's a small graph. Brilliant. So we're no longer doing massive recursion across this huge graph. We've now condensed all these long paths, which are just a single path. We've condensed to 0 length because, you know, there's no point doing recursion for each step of this path if you know exactly where you're going to end up. So we've condensed all these edges. So now the graph is tiny. Now run the backtracking algorithm on that. Why are we... Stop. Result. If start equals goal. Are we visiting the goal that often? Stop that. No, that shouldn't be none. Longest equals none. Alright, something else is wrong here then. Okay. For neighbor in... Let's just do this. For graph.getNeighbors, graph.getNeighbors start. Alright. If neighbor in visited, then skip this one. Alright, run the algorithm recursively on neighbor to the goal, but not... We visited the start now. Distance equals... Yes, start to the neighbor, that's correct. Should we print some stuff here? Print B, D. Do we get anything out of this? What the... Right, stop. Well, neighbor in graph. Okay, just print neighbor. Do we even get neighbors? What's going on here? We do get neighbors. Okay. B equals backtracking, so we're using recursion from the neighbor to the goal using this new visited set. Did I? Yeah, that's fine. Backtracking, neighbor, goal. Did we not... Were we just not able to find a path to the goal? Alright, check edges again. Maybe we don't have a path to the goal. So we want... Alright, print graph.edges from the goal. 131, 133. That makes sense. Okay. Print edges from here. So one of them is the goal. Right. Print edges from the start. One. Print edges from here. One is the start, and then we've got two more. Okay, so it looks like the edges sort of work. Longest is none. So that's meant to be infinity, essentially. Can we just say 0? Does it matter, all this none stuff? So longest equals max longest b plus d. So that would be d to get from start to neighbor, and then b to get from neighbor to the goal without visiting start. And if that's longer than what we had before, we get the longer one. And then just return longest. Will that now do something? Okay, okay. We're getting numbers. Those are too small. We're talking about a bigger graph here. D is supposed to be... Uh-oh. Did I not put the distance right? This should be like in the hundreds. Or bigger numbers at least. Well, maybe that's about right. No, it's not right. I'm not finding any path to the goal. That's... God. B equals backtracking neighbor. Alright. If B is 0, continue. That means we couldn't find any path to the goal, so just skip that one. Why is it all zeros? Let's print some stuff here. Print neighbor B D. Stop printing this. Print neighbor B D. What? We're never even hitting this line. If B is 0, continue. We're always getting zeros. Why? Result equals longest. Oh, wait. What happens if we get to goal? I think the problem is when we get to goal, 0 is a valid number here. Take that out then. I don't know. Ah. We do need nuns. Okay, go back to using nuns. Because 0 is a valid number. Oh my god. B equals backtracking. If... Alright. If B is none, then continue. Because that is... There's no path to get to the goal. So skip that. Alright, so D is... Alright. If longest is none, longest equals B plus D, else longest equals max long, whatever it was before B plus D. Alright, do that now. Still nothing. Why? Add edge U V D U V. We've got none for every single distance. What the heck? We disconnected it somehow. So I think the checkpoints are correct. All right, for each checkpoint, if neighbor in checkpoints, so we add an edge between checkpoints to this neighbor, distance checkpoint plus 1, that's correct, and then continue on to the next neighbor. I think the graph is fine. Something is wrong here. We shouldn't be getting none. We'll be getting something. Shall I just draw my graph visually, see if it actually makes sense? I don't know. Now that we know how to use graph viz. How did I do this before? 20... Is it here? For you neighbors in graph dot edges so items. So we're adding how do we do this? Dot edge, okay. Dot edge, let's say u dot for v in neighbors. Draw an edge from u to v. But we want just cast it to a string or something, I don't know. I think it automatically does that anyway. And then dot render. Alright, what does this look like? What the heck? Yeah, okay, so that's what it looks like. You start from the start, and this is a bidirectional graph, so where's the goal? There's the goal. So that looks fine, it's connected. You can get from the start to the goal. Can we add a label? Also, can we make this a normal graph that's not double-edged? All right. Label. Not label. I don't know. Can I just wanna... Just wanna know what we can do. Caption to be displayed near the edge. It's a string. Graph.dist. Oh, yeah. Got to cast it. Okay. Alright, what does this look like then? Oh, this one. God damn it! Why are these edges distance 1? That's the problem then. It shouldn't be. How the heck did that happen? Distance. Oh my god. That should be current. Was that was it? That was the error. There we go. Now we've got distances. That looks like a correct graph now. Where's the exit? Because still don't want these double edges. Suppose it doesn't matter. Where is the start? There. And the goal is somewhere else. Okay. Alright, fine. So the graph is probably fine. Still not finding any... God damn it, still none. I mean, that was a major error, but... even with distance 1, it should have found stuff. In fact, it should have been simpler. So... Can we make it so that there's... directed false. I don't want double edges. Alright, it doesn't matter. We've got the graph correct now, I think. Now the problem is something wrong with this backtracking. Alright, so... longest equals none. Alright. If B is none, continue. What happens if we are at the goal? We're supposed to... I think we've not... Oh... I removed this. This is the base case. It's supposed to do... that. There we go. We're getting some numbers now. All right. Stop. Should I just print length of visited? I just want to see how many we visited, but this is not reflective of the actual... It's quite a lot. Okay, stop printing stuff. Let's just let it run. See if it actually finishes. Alright, just leave it for a while. This is as good as I can get it, surely. I mean, can we cut it down any further? I doubt it. What more could you do? I've condensed every long path to a zero length path. So it's now just a graph representing distances. And we're walking on this graph of... There we go, 6298. Correct. Oh man. That was a good problem. Good textbooky problem that I failed to do, but that's classic. That's just classic algorithm. Longest path it's an NP hard problem, but you know, for subclasses of well, if the input has certain properties, then you can be clever about it. That was still NP hard, but it was small enough that we could use backtracking. Backtracking is exponential because you're trying every possible turn. But if you condense it to that graph, then you are no longer backtracking along every individual point along a long path. You're skipping paths if you know where you'll end up, because there's no point recursing over those smaller sections. So if you get the graph of distances, then it's manageable. Okay. How long did that take? Oh, only 2 hours. It felt like so much longer. Man, I am not on point with some of these problems. That's my strength. Graphs, graph theory. I mean, I studied graph theory. I researched graphs. It shouldn't be taking me 2 hours. All right, well, it should be taking me 7 minutes. No, not 7 minutes. Bloody hell, that's pretty quick. Okay, 38, that's quite high. Like, in an interview, this is a classic graph algorithm question that you could get in an interview. So in an interview, you'd be able to do that within the interview of like 45 minutes or so. But that's usually not having to code it up fully, but sometimes you might. So you're kind of expected, at least for tough interviews, to be able to do that within 45 minutes. So I guess I would expect top 100 to be quicker than that. Because then you get to copy and paste in libraries you've used before, like Dijkstra and backtracking and stuff. I guess the bit about condensing the graph might take a while, but then that's a common thing to do, so that you should have code pre-prepared for that. I don't know. Cool. And really? I was the first out of... Oh no, that's my private leaderboard. We don't have as many people here. Captain Coders? Oh, people are still doing it. Interesting, okay. I thought this wasn't hard, it's just I messed up my graph so badly. But then you just write recursion and the recursion just works. I wanted to write backtracking the iterative way. Well, not the iterative way, it's just using a custom stack, because that's how I originally wrote it when I first learned how to program. And it was one of the most horrible pieces of code I ever wrote. It's an absolute mess, but it worked. So I wanted to revisit that iterative approach, but write it much cleaner, but I couldn't figure it out. I guess you need tails. You need to keep track of where you've just been. Whereas pure recursion just does that for you. That's why it works. Okay, whatever. Yeah. Okay. Almost there. I still have to finish off 21. 21 is giving me so much headache. It's just... Okay. I think offline I'm gonna have to sit down, do all the maths again on paper, make sure it's alright. And then tomorrow I will tackle it again, but I'll try and do, the proper testing approach. So start small, build up some bigger graphs, solve them using brute force, compare that with my algorithm, see if we get the same answer. Try and figure it out, without rushing things. Yeah, so 21 from this indicate more people attempted it, but a lower percentage completed part 2. So that indicates that it's hard. Oh man. Yeah. Okay. That was a good problem. Good practice. That's such a textbook thing, and I cocked it up big time. Wait, but what were the mistakes I made? The mistake was very trivial. I just forgot to put the base case in, the goal check. Then if you don't put that in, then it has no notion of what goal is. It doesn't know what goal is. So you need to put that base check in. I forgot that. And what else? The other mistake was just a very stupid thing, just putting this current checkpoint instead of current. That's the problem when you name variables both beginning with the same letter. Whatever. They were very minor mistakes, but yeah, that's what happens. Thank you, GraphViz, again. GraphViz helped me spot one of the issues, so yeah, I should be using GraphViz. How do you... I don't want to add edges twice, but I can't be bothered to manually check if I've already added an edge. But there's probably a way to tell GraphViz to ignore duplicate edges. Like, there's probably a boolean called ignore duplicate edges or something like that. Like, I don't know, ignore, no, I don't know. But yeah, so that size of that is 1, 2, 3, 4, 5, 6, 7, it's like 30 or something, 40, 30 to 40. So yeah, that's very backtrackable. And the visited set is small. That's the key. That was why I wanted to do iterative backtracking, because then you don't have to be passing visited around. That was the problem with recursion. I have to look up how to do that again, because that's really the better way to do it, not recursion. You want a visited set that you can just kind of... You want to use the breadcrumbs approach, so you know where you came from. So you're supposed to record some sort of came from map as you go along. And then you can discard things. So then the visited set, you don't have to keep rebuilding it, but you just remove or add as you're going back up or backtracking or going forward. Anyway, enough coding today. Oh man, I hope I finish 21 in time for Christmas Day. Otherwise, it's going to be one sorry Christmas just doing algebra. Reminds me of when I was in university. All right. Thanks for watching. See you tomorrow. Yep, bye-bye.